Santino, how does electricity work?
Well, let's think about it like this. Have you ever used one of these super soaker squirt guns to squirt your brothers before?
Yeah.
All right, so whenever you pump it up, you build up pressure in the water. Well, you can think of that pressure as being like voltage, and then you pull the trigger and you squirt them, right? So you can think of the water flowing out as being like current. So if you can understand these two basic electrical terms, you can understand electricity as a whole. We actually have a cool water analogy demo here at the PSEC if you'd like to see it.
Sure.
All right, let's go. Okay, here's our water flow demo. You can see these valves up top that are kind of like switches in your house that you use to turn on the lights. Well, we use these switches to turn on the water flow. And then we have this PLC over here, which stands for Programmable Logic Controller, in order to control these valves. So when I press the button, you're gonna actually see water flow all the way to the end into the spin wheel over there.
Cool, can I push that button and make the current flow?
Sure. Okay, now remember how you pumped up the squirt gun to build up pressure or voltage? So that's kind of like what this demo here is like. So here we have our power source we can think of. And when I close this valve, we're gonna build up water height here. We can think of this water height building up as increasing our pressure. And then when I open the valve, we're gonna get a lot of current flow because we have very high pressure, and then it kind of stabilizes, as you can see. So I'll do that again. And then you see the high current flow. So do you see how voltage is similar to pressure and see how current is similar to the flow of water?
Makes sense to me.
All right. Want to get into a little bit more complicated concept?
Sure, I think I can handle it.
So there's a law called Ohm's law that describes how voltage and current interact. You do multiplication and division in 3rd grade, right?
Uh-huh.
Awesome, okay. So basically what Ohm's law says is the voltage equals the current or water flow times the resistance. So how do you think I can increase the voltage of this system?
Wouldn't you just close that switch a little bit?
Very good, very good. So I close the switch, the height increases or the pressure increases, and then if I want to, I can make a really, really small resistance and get a very, very high current or water flow. So electrical loads in an electrical system are called resistors. So you can think of one of these loads as being like your hairdryer in your house. You're pretty good at this, huh?
Thanks.
All right, so Kendall, here we have our Kirchhoff's current law demonstration. So whenever I open the switch and I allow the water to flow to this T, what do you think is going to happen if both of these two switches are open?
Well, if the switches were open, wouldn't the water split?
Exactly right. That's how the water divides, which is how the electricity would divide in an electrical system. So I'll open the valve and the water will split evenly between the two. And then, if I want to, I can close one of the switches and then all of the water or current will flow through this one. You could think of this as being like plugging in your hairdryer. We open the switch and we take some current or power to power your hairdryer. Sound good?
Uh-huh.
All right, so let's get a little bit more complicated. This we call Kirchhoff's voltage law. So we have resistors in series, okay? So what Kirchhoff's voltage law says is the total voltage or pressure drop across all of them will be the sum of the resistors in series, of the sum of the voltage drops across each of them. So right here I have 0 pressure drop. That's because this is wide open, right? So if I want to increase this pressure drop, what would I do to this resistor?
Wouldn't you just close that switch a little bit?
Exactly. So if I close this a little bit, I'm going to increase my resistance, okay? And I'm going to get a pressure drop or a voltage drop across that resistor. Similarly, downstream, I can do the same thing, increase the resistance, and we'll notice that by closing this one downstream, we actually increased our overall pressure drop as well. We call this Kirchhoff's voltage law.
So what does this part show?
I'm glad you asked. Okay, so this one shows how power flows from the utility company and can go through multiple paths. So here, we think of this as power flowing from the utility. This is a transformer outside of your house, the big green box, and then that sends power to your house, which would be down here, okay? And then we can think of this little box as like a capacitor or more like a battery. So if we want to, we can charge the battery and we'll fill up the level right here, And when the power from the utility is cut off, it can support the load for a while until the water is drained.
Is that like the battery on my iPad I always have to charge?
Exactly like your iPad. So if you have it plugged in, you could be on it forever, and then when you unplug it, you only get a few hours until you have to go back and plug it in again. All right, okay. So, transformer's working, battery's working. Right here is a check valve. This only allows the water from the battery to flow one way. An electrical component that does this is called a diode. It only allows the electricity to flow one way.
Makes sense to me.
All right, Kendall, so this last one looks really simple, looks just like a spinning wheel, but it's actually really complicated. So we like to think of this as a motor. A motor is basically an inductor in an electrical system, okay? So whenever the current starts to flow, it really resists it, and then eventually once it gets spinning, it doesn't take much force to keep it going. So you can think of that as like a gerbil running on his wheel. He's kind of slow to get moving and stuff, but once he gets running, he doesn't have to do much work to keep it spinning. So whenever you get to high school and take calculus, you'll learn about things called imaginary numbers. This is actually a concept based on imaginary power. By the way, if you understand that, you can explain it to some of the PhD guys in my research group at school.
We have a saying here at the PSEC that if you can't explain something to a third grader, then you probably don't understand it yourself. Obviously, electrical systems are very complex, and since you can't see electricity, it's very difficult to teach others about it. We found that this demonstration is a great starting point to explain electrical systems to kids and adults that aren't familiar with electrical concepts.
Kendall, this is what we call a one-line diagram. It summarizes everything we saw today in the water analogy, and you can see the things like the resistors and the inductors and the transformer. Remember all those?
Makes sense to me.
So Kendall, did the water analogy demo help you understand those electrical concepts that we talked about?
Yeah. Oh, by the way, do you have that squirt gun?
No, where'd I put that thing?
Oh, found it.
Oh.
So you're saying if I pump this up, then it will increase the voltage?
Yep.
And if I pull this trigger, then it will make the current flow?
That's it.
To learn more about electrical power systems,
Contact your local Eaton representative to schedule a visit to the Power Systems Experience Center because I quit.